Thank you.
All right. I got ahead of you guys on here that we're at home, so I apologize for that. We're starting with this question. You should have been able to identify the intermediates here. The intermediates here are, remember we have to identify from the things that are gone in the end. So I've got an X here and this X, these guys are going to cancel. They don't show up in the final equation up here. So those are our intermediates. We also have this guy as part of our intermediates because he comes here and he goes here and he's not in the final. Over here, we have, am I presenting? I hope I'm presenting. I'm not presenting. You can't see anything that I've gone through yet. Crap. Present now. Entire screen. Entire screen. Share. All right. So this is what I was talking about. Intermediate here, 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 here. Intermediate here cancels those guys out. My Y here and here get canceled out. And my XY here and here gets canceled out. So those are my intermediates. This is the next one we did. Here you had to identify this. So here you have this for your rate law. This guy can't be it because remember we're going to sub in for E. We would sub AB. So this would be AB2. That's not consistent. Here we have AB, and that's going to get subbed in for E here. So A, there would be two A's and a B. That is consistent. And then here, this is our slow step. So our rate law here would be KA squared, and that's not the rate law. So it has to be this guy. All right. The next one then is here. Are we done matching these up yet? Okay, so let's check your answers here. Okay. Yes, no, bad. Talk about them. So endothermic, you're going to end up with reactants that have a lower energy starting than your products end up with. So if you want to look for endothermic, that's what these are going to be, is an endothermic here. So this is endothermic. This is another endothermic here. Everything else is going to be exothermic.
I think some of our letters are switched.
Okay.
Because so the bottom left one, E for us is a two-step mechanism instead of a one-step.
Okay. So this is a one-step mechanism here, and it's exothermic. F is endothermic with one step. That's this guy. So your graphs are switched around on there? Is that what you're saying? They look different? Oh, these letters are?
Yeah.
Oh, that sucks. Okay, so this guy is going to be endothermic. It's two steps. And the first step is the slow step. So the high step is going to be your slow step. All right?
These are the first, but for that one is the second step and the first step.
The first step, because it's the taller one. So here, the second step would be the slow one because it's the taller one. Here, the second step would be the slower one because it's the tall one. Here, the first step would be because it's the tall one. All right, catalyst then. I think this is supposed to be an arrow in here. Right here. So sorry about that. They're going to stabilize a reaction. They typically will lower the activation energy. They can also turn a one-step into a two-step process. So that's another example of where a catalyst might be useful. So here you'd have a one-step, and now they're going to do a two-step process. Okay. So in acid-base catalysts, a reactant either gains or loses a proton, changing the rate of the reaction. In a surface catalyst, either a new reaction intermediate is formed or probability of successful collisions or increase. This is where I was talking about how we turn a one-step into a two-step. Okay. So then you can also have enzymes, and if you take AP Bio, they'll spend a lot of time on enzymes with you guys. All right, we can use spectrophotometry to determine these and analyze rate laws from this kind of data. And we did this with the crystal violet fading. If you remember putting that into it and then getting, or maybe I had you guys do that as an online lab. Maybe we had to do this as online.
Is that the one where where we put it in the snow and it changed?
No, no.
This is unit 5, right?
Yeah.
Yeah, I think we were quarantined.
Yeah. So I may have had to do this online and given you the data for this. Okay. So which of the following increase the rate of chemical reactions? So see if you can answer that guy. Ready? Good. Okay. Oh. Well, I think I can answer this one myself. Okay, decreasing the temperature would not do it. Increasing the concentration of the products, no. Decreasing the concentration of the products, increasing the concentration of the reactants would do it, and then decreasing the concentration of the reactants. So increasing the concentration of the reactants. What else could do it? Temp and, okay, and one more.
Particle size.
Exactly, yep. Reducing the particle size, so grinding it up, making it smaller, increasing surface area is what you're actually doing there. It's for that one. All right, so big idea 5, thermochem, okay. Universe, system, surroundings. So you guys need to be comfortable with this. This is the system and the surroundings. System is the chemicals that we're working with. The surrounding is the environment around it. Endothermic heat is going to flow to the system. So what's going to happen is you're going to take heat from a source, from the surroundings, and you're going to store it in chemical bonds. Okay, we're transferring energy here. And because of that, since you're pulling heat from the outside, the surroundings that you are in, it's going to feel cold to you. So these are the ice packs. When you get an ice pack and you break it and it gets cold on you, that's an endothermic reaction. Exothermic is the opposite. We're taking heat stored in chemical bonds and they're exiting the system. Okay? Photosynthesis is an endothermic reaction because we're taking light energy and we're storing it in chemical bonds. Cellular respiration is an exothermic reaction. You're taking energy from the glucose and it's exiting as energy that you can use for different purposes. And some of that comes out as heat. All right. Kinetic energy is transferred between particles of varying temperature. That is known as heat energy. Heat flows from particles from higher energy to cold, not the opposite. Okay. When temperature of both particles are equal, they're at thermal equilibrium. Not all particles will absorb or release heat at the same amount. So that the way that we gauge that is by giving the material something called specific heat capacity. So certain things like water have very high specific heat capacities. That's why water takes so long to cool down or heat up versus the metal pan that it's in. Okay? If you put that metal pan on the stove and let it sit there for a minute and you turn that thing on full blast, that thing's going to burn you. But you let it sit for a few minutes and it cools off pretty quick too, doesn't it? Now water, you start that water full heat and you let it go for a minute and it's a big thing of water, you don't even feel it, it's heated up, right?
Now, would that also include like thermal insulation? Like Like the stuff that the fiberglass, no.
Yeah, they have on
What's
those the fiberglass and stuff like that. They have an R rating, which I'm not exactly sure how fiberglass kind of works. That's more of a like tech ed, go talk to them, or physics kind of like we're getting into the physics world there.
Well, was it the aerogel stuff, where it's made out of silica? Or
Yeah.
Silica has
Yeah.
a high specific heat, or
Yeah.
the air inside the
Well,
silica have
yeah, the air has a high specific or a specific heat associated with it too. And then you also have like these mugs. Okay. The reason why these mugs keep things so cold is because you've got metal here, you've got metal on the inside. Between them is a vacuum. It's actually a vacuum in there. So there's no air in there. And so because of that, it keeps that heat from getting in to my drink. So once my drink is cold, it keeps heat. Now it still happens through the lid and stuff like that, and this isn't a perfect system, but because of that, it helps. But that metal is cold. You know, it feels cold because it allows heat to exchange very easily. But water has a very high specific heat. That's why, like, if you go to Milwaukee this time of year and you're down by the lakefront, it can be a gorgeous 85-degree day, and down by the lake, it still feels cold because the water is still very cold in that lake from the winter. Now, the fall is the opposite. You know, it's warmer by the water down there because the water has a lot of heat stored in it. But it takes a long time for the water to heat up and a long time for it to cool down. So that's the specific heat capacity. And when you're working with this, Q is the heat equals the mass times the specific heat value, which they would have to give you on a chart, or they may give you these other things and you have to calculate that, times the change in temperature. First law of thermodynamics, energy is converted or conserved. Good Lord, my brain is gone today. Sorry, you guys. Temperature is a measure of the average kinetic energy of particles in a substance. Energy can be transferred as work or heat. And we have heat plus work gives us our change in energy. And work is also equal to negative P delta V. This is the work a gas does on the surroundings, like when a piston works. Okay. So we have expansion and contraction of the gas. Okay, so we have the pressure value, and then the change in the volume would be your delta H here. Energy changes, chemical reactions involving formation of new products. Bonds can be broken between atoms. And remember, reactants, they're broken, and bonds, they're formed. So broken minus formed is going to give us our value. If that value is negative, it's exothermic. If the value is positive, it's endothermic. Maxwell-Boltzmann distribution. This is a very common thing that you will end up seeing. I'm guessing you'll see this at least once next Friday in some format, this type of graph. Or they may give you, this may be an FRQ kind of question where they'll give you this thing and then change the condition and say draw it in, and you have to be able to draw this guy in. Okay, very, very common, at least comes up in some fashion every year on the test. Temperature is a measure of the average kinetic energy of a sample. Particles with larger mass have lower velocity. So if this, instead of temperature here, we substituted in mass, so this might be neon and this helium, okay? So neon would go slower than the helium, or Lippy would go slower than Rose, something like that. Maxwell-Boltzmann distribution shows the distribution of the kinetic energy becomes greater at a higher temperature. The areas under the curve are equal, and therefore the number of molecules are constant. Increase in kinetic energy is going to show the number of particles with activation energy necessary to react. And the activation energy is not changed with temperature, but may be changed with the catalyst. All right, bond length and strength. This is another common diagram that you will see on there. Remember, the bottom of this is where its most stable form is. Okay. So bond energy is endothermic, the energy needed to break bonds. So the size of the HCl is smaller. So we have 3 different factors here, okay? Size, like HCl is smaller than HBr. We have polarity. So if we look at HCl, is that over here? No, I don't see that over there. Polarity, HCl is more polar than HC. And then bond order, okay? This is going to take more energy to break than this guy. Net energy change during a reaction is the sum of the energy required to break the bonds. Broken minus formed, broken minus formed. Say it with me, broken minus formed. Any bond can be formed, any bond that can be formed can be broken. These processes are in opposition, so their enthalpy changes in magnitude. You just change the sign. So delta H bond breaking is going to be positive, bond forming is going to be endothermic. To find this, remember bonds broken minus bonds formed. Okay. So we've talked about energy, endothermic, and exothermic. All right, heating curves, another common thing on there. Remember, during a phase change, what happens to the temperature? Absolutely nothing. Nothing happens to the temperature. What is happening during that phase change? Well, if they're going this way, they're breaking. If they're free, but they may be reforming if it's going the other direction. So it just depends on which direction, going this way. If you're cooling, then they're going to be reforming. Here, they're not broken here in the melting part. They're just being reduced, okay? Here, they're being broken. That makes sense? Here, they're being weakened. Here, they're being broken. Here, they're forming. Here, they're getting stronger. All right, heat transfer due to temperature change. So we talked about this formula. During a phase change, Q would equal delta H times the phase change. So they'll give you the change at heat of fusion. And then you can also have that at constant pressure. And then when gas expands or contracts, we can use this formula. All right, we talked about salt coming apart. And this is where I kind of lied to you before when I said, it's just a physical change. Well, there's actually some chemistry going on here too, or chemical changes going on here too, because we're changing heat amounts. You also saw that when we mixed the water and the alcohol together. Did we do that together? Mixed water and alcohol and heated. Maddie said yes. Okay, and I brought it around and I made you feel the thing.
Yeah, it was like right beginning of the school year. We had Mr. Phillips in the room when we did it.
Okay.
We had the chlorine discussion afterwards, I think, too.
All right. So, so when these come together, remember our solute and our solvent, they have to kind of move apart from each other. So, because it's bound together as a solute, it's got to come apart. So that's going to take some energy. And then the solvent, the water molecules have to be pulled apart from each other too, which is going to take some energy. So that's going to be endothermic. But when they come back together and the water surrounds it, that's exothermic. And it just so happens that it gives off more energy when that alcohol is mixed in with the water than it required for it to pull those things apart. So that's why that thing felt warm when you were done. Energy is transferred between systems in contact with each other. When these things touch each other, they're going to transfer heat. And you can feel that like when your hand touches the tabletop, it feels cooler. If you touch a hot burner, you can feel it pretty quickly. If you touch your curling iron, Austin, you use your curling iron often. When you feel that it's going to transfer, okay? Whatever's lost by the system is gained by the surroundings. And so we can set equations equal to each other to be able to solve problems then, okay? So we can use calorimetry, and in here we've always just used these styrofoam cups. Did we do one of these labs?
I think we were going to, but
and then life got stupid. Okay. So whatever's lost by the system is gained by the surroundings. So you can set these equations equal to each other, and whatever's lost by one is gained by the other. Okay, so see if you can solve this guy. Ready? B. Did you get B? You got B? Good. Okay.
What's the difference between B and C?
B, too small, too large. Good?
No, but on our paper it says too small.
Yeah.
So it's backwards?
Although C on ours says the calculated value would be too small because the heat absorbed from the ground.
For us, C is the one that's D on there.
All right, so B is the correct answer. So find whatever this says on your paper and circle that answer and then back check it.
It's the same on our paper.
It is right?
Yeah, it's just C.
Okay,
So what
So we're
would
fine.
be the difference between B and up there, D?
okay, what?
The difference is like absorbed versus lost with the surroundings?
Yeah.
Not really good.
Because D's saying like it'd be taking in heat from the room, but it would balance the equilibrium in the temperature with that room already.
Okay. All right. So these are calorimeters, okay? If we know the specific heat of a material, okay, then we can, and that material like is water, for example. So if we know the specific heat of the water, and we take a temperature of the water, and then over here we have a piece of metal that we're going to heat up, we're going to get it boiling in water, in a different sample of water, okay? So if it's boiling in water, and we leave it sit there for a while in that boiling water, what temperature is that metal?
The specific heat of
No. What is the temperature of the metal if it's in boiling water?
Oh,
What is the temperature of boiling water?
I'm trying to think. The 298?
No, it's 212 Fahrenheit. We're not in a Fahrenheit world. We're in a Celsius world. What is the boiling point of water in Celsius for water? Hundred degrees Celsius.
Okay.
Boiling water is 100 degrees Celsius. Okay?
It's like 390.
No, it's 212. Oh, you want Kelvin? It's 373 Kelvin.
373.
Okay?
Well, that's what we usually use.
Well, for specific heat, though, if you look at that formula sheet, they use Celsius in there. And the reason why they use Celsius is because your specific heats are typically given in degrees Celsius. I'm trying to see, they don't have a specific heat listed on here for water. Let's see, specific heat table. And of course, the one that I pull up isn't. Oh, good grief. Seriously? There we go. Okay, so this is typically the way, joules, grams, degrees Celsius. That's the way you're end up seeing it typically. for those values. So with that specific heat given in degrees Celsius, then the temperature on your, when you're working with your samples is going to have to be in degrees Celsius. All right, so if we know that this guy is at room temperature, and then we take a piece of metal that's 100 degrees Celsius and put it in here, that metal is going to cool down, right? Okay, so whatever heat is lost from that metal will be gained by the water. And so we can check the temperature of that water and see how much it rose by, and then set up our equation from there. All right, equilibrium. So when we have a state where the forward reaction and the reverse reaction are constant and equal, that's equilibrium. Remember, the reaction is still running. It's not complete. It's not done. It's just that this stuff is turning into this stuff, that's turning into this stuff, it's turning into that stuff. You got it? Okay, the reaction is constant, but it's still occurring. They will try to get you on that. Okay? Remember that when you're looking at these, your concentration's always raised to the stoichiometric coefficient, and it's always products over reactants. This equation is given to you on your formula sheet. All right, so we've got K is at equilibrium, Q is somewhere along the way. And remember, if you set it up so that you have K and Q, whichever one's greater than, that's the way the reaction is going to run. So always put your K listed first and then your Q. Remember how we did that? That'll tell you which way the reaction will run. So if K is greater than Q, then the reaction is going to run this way. If Q is greater than K, then it runs this way. Oh, you guys have a question here. Oh, so you have to figure out K3. Do you have that question on your sheet?
Mm-hmm.
See if you can figure out the answer. Got it? No? Good? How did you do that without a calculator?
I don't know. I don't think I got the right answer, so I'm confused.
Did you get 2.9?
Close. I got 3.0.
Okay. So these reactions are doing what? What are we doing with these reactions here?
Combining.
Okay.
To some degree.
All right. The CO2, the H2 is here. So we've got to flip this guy around, right?
Mm-hmm.
Okay. So if we're flipping him around, then my
Your oxygen cancel, right?
the oxygen's canceled out, and then these things are left, but they're left to half of the amount that they were, right?
Mm-hmm.
So when we flip that around, we're going to flip this guy upside down then, inverse. So So inverse that guy. And then adding the reactions, we're going to multiply them together. So inverse and then multiply. All right, kinetics then. We're going to examine the rate at which reactions proceed. The rate laws then are used to describe how the reactant concentrations affect the reaction rate. The rate constants are determined experimentally at a given temperature. The equilibrium describes the state at which the rates of the forward reaction and the reverse reaction are equal. If the rates are initially unequal, the system isn't in equilibrium, the faster direction depletes the reactants, which feeds back to slow down that direction. At the same time, the slower direction accumulates the reactants, speeding up the slower direction. Eventually, they loop until they become equal. The rates, okay, become equal. And that's when your equilibrium is established. Okay, in the graph over here, after equilibrium has been achieved, additional hydrogen is thrown in there. So that's going to increase our reaction rate for a while, but then eventually we're going to reestablish our equilibrium. All right, K versus Q. Again, I flip this around and I do K versus Q instead of Q versus K. Because if you put your K forward, then that's going to always tell you, if you know which one's bigger, it's going to tell you which way the reaction is going to run. So I don't like this. I don't like K versus, I like K versus Q, not Q versus K. Okay? And I think it's so much easier to set it up that way. All right, calculating K. We've got equilibrium constants. We're going to write an equilibrium, an expression here, determine the molar concentrations, and then substitute in those quantities. So calculate K for the following systems, and then try to figure out what your value is here. So by the time you come in on Monday with you guys, I want this packet completed. Okay? So go through, complete the packet, and this is where we're going to, I'll start up with the lecture tomorrow here, but I want everything in that packet that's not covered by Monday so we can talk about it, okay? And the slideshow is online, so if you get stuck and you need to go back and look at it, go on there so we can talk about this, okay? And Addison, what are you doing after school today? Okay, can you come by here and make sure that I have this thing taken care of for you before you leave?
Yeah.
Because I've got that